Hello everyone and welcome to our webinar on health economics and outcomes research with Bayesian networks and BayesiaLab. Thank you for joining us today. Let me start off by taking you through today's program. I'll quickly introduce our team and our technology. Then I'll provide some motivation and background for today's examples. While we're talking specifically about healthcare and the public policy domain, it is ultimately all about distinguishing correlation and causation. And for that purpose, we'll have two examples to illustrate that. The first one is about a public health campaign in Chicago, and that's our introductory example. And then we will proceed to the economic evaluation of imaging technologies. More specifically, we will talk about MRI scans versus CT scans and their long-term cost. So let me introduce today's webinar team. On the line with me are Stacy Blodgett, Customer Relations Manager, and Claire Gora, who is our Director of Sales. Finally, my name is Stefan Conradi, and I'm the Managing Partner of Bayesian USA, and I will be taking you through today's program. So, you will hear the term Bayes a lot today, so please allow me to clarify some terminology. Bayesian, that is our company. BayesiaLab, that's our product. That's what you will see in action today. And then Bayesian networks, that refers to the paradigm invented by Professor Judea Pearl. That's what everything you see today is based on. But the software BayesiaLab, I should say a few words about it. That's a desktop software for encoding knowledge, learning Bayesian networks, editing them, performing inference, analyzing, simulating, and optimizing, all using the Bayesian networks paradigm. And we will see quite a few of these functions today. But BayesiaLab doesn't stand on its own, even though it is our core product. There are several other components that are part of the BayesiaLab software platform. There are web applications such as the Bayesian Expert Knowledge Elicitation Environment. We have APIs, we have code expert modules, we have educational packages, and of course we have our book. And that remains available for free download, but it's now almost 2 years old, so we're now working very hard to get the second edition out. So that's one thing I've committed to for doing this summer is catch up with some of the chapters that need to be rewritten. In any case, as always, you will receive a download link with all the slides, the data, the networks, and the recording of the webinar itself after today's event. Usually we send it out a couple of hours after the webinar ends or sometime this evening. So let's get to our background on motivation, and I would like to frame up today's discussion by quoting President Obama, who said the following at a conference of the American Medical Association back in 2009. He said, "Less than 1% of our healthcare spending goes to examining what treatments are most effective. So one thing we need to do is figure out what works and encourage rapid implementation of what works into your practices." So that was obviously all said in the context of Obamacare, etc. And President Obama's comments were very specifically focused on medical treatments, but I think it is fair to broaden the objective a bit and to apply this objective to healthcare policies and public health policies in general. And taking a quick look at this somewhat provocative diagram of how Obamacare works, figuring out what works is not very obvious. But interestingly, complexity is not the problem in terms of understanding what works. Much rather, what we need to realize is that what works is a causal question. And it breaks down into two separate issues. The first one is effectiveness, and the second one is real-world efficacy. And the issue today is not about effectiveness, because we know effectiveness can be very well established with experiments and clinical trials. So in fact, I've read somewhere that the FDA is currently tracking 126,000 clinical trials. Sounds like a very big number. But in any way, that's the gold standard for establishing effectiveness, for the gold standard for establishing causality. The problem we are facing today is real-world efficacy. Why? Because we can only observe the real world, and observational studies can only produce correlations. And we all grew up with this mantra, correlation does not equal causation. We hear it over and over again. We probably say it, sometimes we may ignore it, but if there is such a thing as a consensus among scientists, that has been one for a very long time, and I'm quoting here Professor Terence Speed. At the time, I think he was director or president of the American Biometric Society. He said, considerations of non-experimental causality should be treated as they always have been treated in statistics, preferably not at all. Now, Judea Pearl, our hero, he said that this is really one of the biggest impediments in scientific progress, because if we just limit ourselves to statistical inferences and not address causal considerations or explore causal relationships, we're really limiting our potential for insight. And this is really the challenge we want to discuss in this webinar. But before we get to our first example, I need to share some caveats, and that is, all subject matter presented in this webinar is strictly for methodological illustration purposes. So the problem domains I share about public health policy and health technology, these are really merely examples of using Bayesian networks. And all the numerical values you see throughout this presentation, you should consider as fictional. And really, absolutely no part of this webinar should be interpreted as a research finding or a policy recommendation. So let's get to our first example. As I said, we're going to look at efficacy. And in this first example, we're looking at the topic even more broadly. It's not just about healthcare treatments, but more generally about health or about public health policies. And this first example is about a public education campaign in Chicago promoting safe sex. This campaign ran in 2015 and was titled Chicago Wears Condoms. So, and beyond advocating safe sex practices and birth control, it also encouraged people to get tested for sexually transmitted infections. This campaign was aimed at teenage and young adult residents of Chicago, and it seems there was an apparent focus on underprivileged and minority groups. Now, so far everything that I've said is a historical fact. This campaign actually did happen in 2015 in Chicago. However, what now follows is a fictional example based on this real background. This also means that the data you will now see is synthetically generated. For all I know, it is possible that such a study exists, but we certainly don't have access to it. So here goes our story for the purposes of this example. At the conclusion of this campaign, Chicago Wears Condoms, the Department of Public Health conducted a survey of 1,000 young adult residents of Chicago to understand the impact of the campaign. So they asked a number of questions, such as the first one being, have you seen any campaign materials? Just a binary variable, yes, no. The second variable, you can see that in this table to the right, is about housing, where people live, public versus private. Now, that was not directly asked, that was rather inferred from the respondent's address. Third question was, have you been tested for sexually transmitted diseases in the last 3 months? And so finally, the last question, the principal objective, have you consistently used protection in your sexual encounters over the last 3 months? Those were the questions. And you may perhaps wonder, well, why housing? Why is that important? Well, they are using that as a proxy for socioeconomic and minority status, public housing versus private market rental or condo. So now they got the results back from the survey, and they're being presented to the health commissioner, and it doesn't look good at first glance, because what appears to happen is that among those folks who have seen the campaign, who have observed the campaign, their use of protection is lower than the use of protection among those who did not see the campaign. So that's obviously not very encouraging, but we should not be surprised. Perhaps this was counterproductive. Perhaps people say, I won't let government overlords influence my lifestyle. Who knows? And it certainly wouldn't be the first time that a well-meant government program backfired. So what does it leave us? Well, of course, it would be political suicide to release such information to the public. So what we'll do, we'll massage this data a little bit until the numbers look better. And sure enough, if we now take the very same data, the 1,000 responses, and stratify on housing, it seems like condom use is going up in both groups, among the people who live in public housing and in private housing. So how is this possible? How can it be that when we look at the group as a whole, condom use declines, and if we look at them separately in each subgroup, use increases? Well, that's yet another example of Simpson's paradox. Simpson's paradox is this phenomenon in which an effect appears in subgroups of data, but it disappears or reverses when these groups are combined. So that's what we're encountering here, but we're not done yet. It keeps going, because now we're taking the same data set and are introducing the STD test as another covariate. We're stratifying on that variable. And now it looks really bad, because now the condom use goes way down in both subgroups. So it's all bad. But if we now finally introduce all variables, stratify on STD test and housing, and if we look at all the increases and decreases, it seems like everything cancels out. So what is it? What was the campaign's impact? Was this a good use of resources? What are you going to tell the mayor who had approved millions of dollars for this campaign? Of course, the mayor says, well, what does the data say? Well, we've been there. We've just gone through all the data. We have analyzed it backwards and forwards. Data alone cannot give us the answer here. We need to look at things differently. And here I'm bringing back our very popular map of analytic modeling and reasoning, and you've seen this many times before. It shows the major distinction that we need to make between the left and the right side of this map: association, correlation on the left, and causation on the right. We need to distinguish between given that I see versus given that I do. Given that I do is a causal question, and what we have at hand here is causal. What was the effect of doing this campaign? Did we cause to increase safe sex practice? That is the question here. But what we have is not on the right side. Rather, what we have so far are purely observational models. We actually have 4 of them. Just learn from data, done crosstabs, etc. So they are all in themselves correct, but not really what we need. Where we need to be is here in the bottom right-hand corner. We need a causal model to answer our question. And more data or fancy statistical techniques don't get us there. Instead, what we need is theory. We need to have external knowledge, domain knowledge, and introduce that into our model in order to get to a causal model so we can perform causal inference. And that, of course, is one of the motivations why we want to use Bayesian networks, because Bayesian networks allow us to cover this entire spectrum. On the one hand, we can machine learn network models from data. On the other hand, we can also formally introduce our own causal model. So that's what we want to do now. And So let me start here, or let me rather reiterate that. Once again, it would be ideal if we could run an experiment. That would be really the gold standard for getting to causality, answering our question, was this campaign successful? But of course, here we can't do that. We're years after this campaign happened, so all we have is observational data. So we need to pursue alternative paths to get to causal inference, and we will explore both of the blue and the gray path that you see here on this chart, and both involve theoretical knowledge, just at different points. But perhaps let's start with the blue path here, where we start with an expert-defined causal Bayesian network. So we will look at the variables that we have: housing, campaign exposure, STD test, and in use of protection, and we need to hypothesize about what the causal relationships are here. And now you may say, hold on, I've seen this before. This looks like just the same example that we did a few weeks ago in the marketing mix webinar. Yes, but something is a little bit different. So yes, your deja vu is correct, but we're actually now going sort of pursuing something else, or we'll encounter a different situation, because initially things will go very smoothly. We will look at these variables and we will assume causal relationships, and they seem all very, very intuitive. So we will do that for now, and then we will see where things start to fall apart. So here I'd say housing and campaign exposure are causally related. And I would say housing, where you live, influences whether or not you're exposed to the campaign, because the campaign had posters at bus stops and subways. So if you perhaps live somewhere in the affluent suburbs, you would perhaps be less exposed to such campaign posters, etc. So that's my hypothesis. The same way, perhaps housing, where you live and what socioeconomic strata you are, depends on whether or not you would do an STD test. So that's my second assumption. Same thing with housing and use of protection. But it could really be, I'm not saying whether it's positive or negative. It could be that, in certain neighborhoods, condoms may be less easily available or less affordable to certain disadvantaged groups, or they're perhaps more easily available because high schools hand them out. Who knows? So the influence could be positive or negative. What I'm saying is that the influence couldn't be reverse. Whether or not you use a condom probably doesn't change where you live. So Perhaps we can agree on these three arcs, and then you may think, well, let's just keep going here and complete this. This should all be fairly straightforward. But here I'd like to challenge you. Well, is this the complete graph? Is it that campaign exposure is the cause of protection, or is it that doing an STD test then makes you use protection? Or could it perhaps be that one? Could it be because you're not careful, you're not practicing safe sex, that then you are considering to take a test? Or could it perhaps be you took a test, you perhaps have something, and then you're particularly conscious about all the banners on that topic? Perhaps that, as an issue is perhaps important to you, you all of a sudden become very sensitive to all messaging in this regard. So here I would argue we can't really resolve it. We can't really know which direction does the R go. Is it from campaign exposure to STD test, or is it the other way around? So there are numerous options. So we're kind of stuck here. We cannot with certainty establish the causal network, and therefore the blue path that I have highlighted here is not an option for us right now. Otherwise, unless we make those certain assumptions and say this is how it works. So we're going with the gray path here. We're going for a different kind of theory. We are introducing our theory later. And we can do that because there is what is known the disjunctive cause criterion. That is a new criterion for confounder selection because it helps us to correctly identify the confounders even if we don't have a full causal model. So we have the advantage that we can machine learn a statistical model, use this criterion to select the confounders in order to then estimate the causal effect. This criterion is very, very simple. I'll just read it to you. It says, we propose that control be made for any pre-treatment covariate that is either a cause of treatment or of the outcome or both. So in our case, the campaign exposure would be the treatment, the use of protection would be the outcome, and then any covariates we would declare as confounders. And once we have that, once we have defined these variables, then we can use BayesiaLab on the basis of a machine learned model to perform direct effects analysis, which involves likelihood matching, and that gives us the causal effect that we're looking for. But what is very important here, we need to furthermore assume that there are no unobserved confounders, that there aren't other variables that influence behavior like gender, education, income. These would be very bold assumptions to make, and I'm not claiming that these assumptions hold. But everything we do from here on out is based on this assumption. So let's apply the criterion to the example and to the variables that we need to classify. So here the question is housing, first of all, a pre-treatment variable? Yes, I would say yes, it is a pre-treatment variable. The next question is it a cause of the campaign exposure? And we already said yes earlier. And in that case, I actually don't even need to keep asking, because with that, if I say yes the first time, it immediately becomes a confounder. So that's very, very clear. So I don't even need to ask whether housing is also a cause of the outcome. When I say cause of the outcome, I mean potential cause. So I should always add that because we won't know how big or how strong that cause is until we actually estimate the effect. Okay, let's move on to the second one, STD test. Is it a pre-treatment variable? No. So with that, it's immediately nixed as a confounder, and we have to declare it as a non-confounder. So we don't even need to think about which way could campaign exposure cause the STD test or which way it goes, since it is not a pre-treatment variable. It's a non-confounder. So with that, this is all the theory we need, plus, of course, no unobserved confounders. We always need to keep that in the back of our heads. So let's now switch to BayesiaLab. Okay, BayesiaLab should appear on your screens momentarily, and I think here it is. So we now take the data set from our survey from the Chicago campaign. I've prepared this data set, opening it up. Here is the first step of our data import wizard. Here we see the 4 variables in the form of columns. They're all categorical, so there's not much we will need to do. No missing values, so no discussion required in this regard. And we don't need to perform discretization since they are all categorical. So I just need to bring in those variables. Here they are. I'll make these a little larger, and I'll change the layout for reasons that will become clear later. So, okay, so here we have our 4 variables. Use of protection, that's ultimately our target node. We want to see how campaign exposure in particular affects the use of protection. So we don't have a model yet, and as I said earlier, we don't really know the true theoretical model. If we knew it, we could just draw the arcs and then estimate the parameters. Instead, what I will do is I will declare use of protection as my target node, and now learn an unsupervised, a supervised model with the augmented naive Bayes learning algorithm. And here it is, and it certainly looks entirely counterintuitive because the arcs are outbound. They go out from use of protection towards the other node. Clearly not causal, but as I said, we don't need a causal model here. We merely need a model that captures the statistical relationships between these variables, and our theoretical knowledge comes in through the definition of confounders and non-confounders. So we don't need to mess with these arcs. We can just leave them as they are, keep the model as it is, and merely now tell BayesiaLab what's a confounder, what's a non-confounder. In fact, by default, all variables in BayesiaLab are confounders. So rather, I need to declare what is a non-confounder. So here in our case, it is STD test. So I will formally add this to the class non-confounder. So I'm setting this by adding this to this predefined class, and now it is a non-confounder. Now, as I run my direct effects analysis, which I will do very, very shortly, that variable will not be matched on. So, okay, we are ready to proceed to our effect estimation. First, of course, I need to go into the validation mode. I simply go to Analysis, Report, Target, and now I select Direct Effects on Target. This means whenever I'm using a direct effects function, you see this total effects versus direct effects in many places throughout BayesiaLab. When I select direct effects, this means that I'm invoking likelihood matching. So let me run that, and then I will show you precisely what is happening. Direct effects, in this case, I'm only interested in the effect of campaign exposure to use of protection. And here is the result. Here is my report. It says that the unit effect of campaign exposure is 0.0365. So there's roughly a 4 percentage point increase in condom usage as a result of this campaign. This is the direct effect we have estimated now based on the theoretical assumptions that we make. Here I've computed this with the direct effects report. I can also go through this in a more manual way. I'm bringing up the monitors for these 4 nodes, and let me just kind of reorder them a little bit. Put campaign exposure to the top, and now I can replicate what I just did through the report. I can replicate that manually, and that is I can fix the probabilities on our confounder. That's what we need to match on. I right-click on housing, say fix probabilities. With that, I have matched on it, I have conditioned on it, and now I can toggle back and forth between campaign exposure, yes and no. And if you now look at the bottom, the use of protection, there we have exactly the difference that we computed earlier with the direct effects analysis. So as it turns out, given the assumption that we have no unobserved confounders, it appears that this campaign actually had a positive impact. So with that, I would like to conclude this particular example and return to PowerPoint and switch gears altogether. Again, give me a few seconds to make that switch. Okay, so totally different topic. Now we're going to evaluate medical imaging technology. That's our example 2. And we hear about this all the time, cost of medical devices, advanced medical procedures. So whether we want to explore now whether such advanced technologies are always worth their cost. More specifically, what we want to do is compare CT scans and MRI scans. CT scans refer to computer tomography, MRI scans, that means magnetic resonance imaging. So CTs work with X-rays, while MRIs, as the name implies, work with magnetic fields. And there would be a lot to say about the technical differences. I certainly would not be qualified to speak to that. However, what is commonly known is that MRI scans are quite a bit more expensive than CT scans. So now the question is, are they worth it? I mean, the more complex technology has for certain types of diagnosis may have some advantages. Are they worth the premium in general? And so somebody may ask the hypothesis, somebody may say that the cost premium of MRI scans is offset by cost savings generated through better diagnosis and more appropriate therapies. Yes, I'm thinking about theories too much here. Therapies, I mean. And that may make sense. You think you have more accurate diagnosis, it's less trial and error. You get to the point, you treat the patient for what actually ails him or her, and therefore that leads to long-term cost savings. So the research question here is, does the systematic use of MRI scans cause the reduction of the long-term cost of therapies? So let me now share this with you visually. So a bit more formally here, we think of MRI scans as a treatment, and then the CT scan as the control group. Both scan types lead to diagnosis and therapies, and in the end, the treatment effect would be the difference in total cost in dollars, as measured in dollars. So, how can we answer that question? Again, it would be ideal if we could perform an experiment. And perhaps in this domain, it wouldn't be entirely impossible. but it would certainly take years to implement. Rather, what we have is we have observational data from many years of using MRI scans and CT scans side by side. I believe most hospitals would have both types of machines. So there is lots of data. And since we can't run an experiment, what we need to do is pursue, once again, one of the bottom two paths, the blue one or the gray one. So here's our data. We have 25,000 commercial insurance patients who've had either an MRI scan or a CT scan. And for those patients, we have literally millions of patient interactions recorded, including tests, diagnosis, procedures, payments, office visits, inpatient days, outpatient visits, literally hundreds of variables with all the treatments and procedures and the diagnosis coded by ICD-9 code. That's the code that classifies diseases and conditions. So we have a wealth of information. And before we go into actual model building, let me share with you the structure of the data, how we're going to set this up to make the analysis possible. So here is the data structure. Here is a fictional patient, Mr. John Doe, age 47. And on the left side of the slide, you see this blue panel that shows all the costs that this patient incurred before the scan. So we have this recorded in time slices, t minus 16, minus 59, 58, all the way to day 0, which is when the scan happened. And then in the pink panel to the right, there we have recorded all the costs by day after the scan. And this actually extends to an entire year before and after. In fact, we have data for 3 years before and 3 years after. And so just as an example, or one more thing, and by row for this patient, we see what category, what ICD category the individual cost was associated with. So here, for instance, on day T minus 59, this patient incurred charges of $745 related to neoplasms. So it's some kind of growth. Then again, on day T plus 1, this patient incurs $3,148 in charges related to the same ICD category. So that's what we have for each patient, but we have to roll this up to make it manageable. And this is what you see in this particular slide. So we now have one row per patient. The first column shows member ID, the insurance number, which in this case is a fictional number. Then we have the imaging type, MRI versus CT in the second column, age in the third, gender in the fourth. And then what you will see in each of the columns is the cost per ICD-9. So we have the total costs per ICD-9 category recorded for each patient before the scan, which you see on the screen here, and then off screen to the right would be all the charges per ICD-9 category after the scan. Again, this is what you see here is fictional and synthetic data. It relates to a true study, but of course that data cannot be made available. So this is kind of a synthesized version, sort of related or conceptually related to this original true study. So, okay, how do we go about this? Now, given that we have so many, and perhaps I need to go back here one slide, given that we have so many ICD-9 codes, clearly these ICD-9 codes are not independent of each other. So, for instance, if you think of elderly patients that go to a hospital because of hip fractures, it is not uncommon that they develop pneumonia, and then they may develop bed sores. and perhaps other ailments related to that. So then now the question is, what causes what? Is it the pneumonia that causes the bed sores indirectly, or is it the hip fracture? Or in which direction does the causal arc go? And with hundreds of potential comorbidities, I would argue it is once again impossible to create a theoretical structure that tells us what causes what. So what we originally intended to do in Chicago by creating an expert-defined causal network and failed there, we can't do here either. So we're stuck. Once again, we need to pursue the bottom path here and generate a machine-learned Bayesian network, and then, as we did before, apply the disjunctive cause criteria. So here is the conceptual model, just with three cost variables, pre-treatment and post-treatment. In the real example, we have hundreds of them. So here I'm just showing three as kind of symbolically, if you will. And all the pre-treatment costs we are considering as confounders. As we discussed earlier, these are the ones, and here in this case, pre-treatment is very obvious. It's already contained in the name of these variables. These exist before the treatment happens, MRI versus CT scans, and then everything else happens post-treatment, and inevitably they need to be non-confounders. So what we're going to do now is simply take all these variables, all their data, machine learn a network, including the target variable outcome, and I should mention here the total outcome variable is simply the sum of all the post-treatment costs. So our question is ultimately, if we systematically do a CT scan versus an MRI scan, what is the cost difference in total at the end of 1 year? So that's what we want to do now. Here is the workflow that we're going to pursue. We start with data import, and then I'm going to do a few things that are not necessarily essential here, but as always, I'd like to highlight some interesting features of BayesiaLab or some practical features. And here in this case, instead of performing discretization ad hoc inside BayesiaLab, I have defined a file offline with the bins for my variables. So I'll show you how we can import that. That's sometimes very, very practical. Secondly, given that we have so many nodes, we will associate a node position or node location dictionary. This way we can always get back to exactly the same layout on the screen. Then we do confounders, non-confounders, their assignment, and then we proceed through the learning until we get to the target direct effects analysis through likelihood matching. And on that one, I should say a few words before we switch back into BayesiaLab. Because, yeah, I think likelihood matching just needs an intuitive or more intuitive explanation. So here we have three of our confounders, our pre-treatment variables. And so we have age, the ICD-9 spend for musculoskeletal system and connective tissues, and the ICD-9 category for neoplasms. And what you see here on the left is the distributions of the patients that had a CT scan, and then on the right you see the scan type MRI. And if you look closely, you can see that these distributions are not identical. So the treated and the non-treated in this case are not comparable. So that's the whole objective of matching, that we make them comparable. That's the objective of conditioning, of stratifying, whatever method you use for conditioning. Here we use likelihood matching from these, moving from these not comparable distributions to comparable distributions. That's what BayesiaLab does. It's actually a fairly demanding algorithm that has to run in the background. And what I should point out, we're not just doing this for 3 variables, but in what you will see for around 20, and in the real world study, we are doing this on hundreds of variables, performing likelihood matching on hundreds of variables simultaneously. So with that, let me switch back to BayesiaLab. Okay, there it is. I'm now going to bring in my data set. And here, this is it. Once again, this is synthetic data. So this way I will be able to share that with you after the webinar. Here we see in the columns, the first one is scan type, then we have age, gender, and then for each ICD-9 code, we have the pre-scan cost. And as we scroll further over to the right, there you will see the same ICD-9 categories again, this time with the post-scan cost. Let me bring this in. Here we see what variables are categorical versus numerical. Very straightforward, nothing to change. No missing values. That makes our life easier. But the next one now, this is where we now look into how we should discretize these variables. You know, here, for instance, here is our distribution of age. And I could use one of the discretization algorithms, or what I will use instead, I will load a discretization. So this was the file preview you saw earlier. Oops, did it take it? What's happening here? Here we go. Yeah, it did take it. It just, here you now see the discretization we loaded. And as I said, if you perhaps repeat your import many times and experimenting with different settings, then it's easy to define the discretization once and for all, save the thresholds, the discretization thresholds, and then load them instead of redefining them each time. Okay, with that, let's bring in the data. I think we have 25,000 observations, so this should just take a short moment. Okay, here we are. Now I have to admit we have very long variable names here, so all this is running into each other. Helpful function here is the staggered layout, which kind of offsets the nodes a little bit. But given that these variable names are so long, I really need to spread this out to make this legible. So what I want to do next is assign these nodes to classes. So I've also done a little bit of pre-work here. I can now load a dictionary with the predefined class assignments. Or in fact, you know what, we've got a little bit of time. For once we're not running behind schedule, I will show you how we can assign in this large number of variables, how we can quickly assign them and group them into classes. So what I will do is I would like to group all pre-treatment variables into a single class. So I'm typing into the search box, which I activate with Control F. I search for all these pre-treatment variables. I highlight those. And you can now see how BayesiaLab has highlighted all of them. And while they are selected, I go to into the contextual menu, properties, classes, and I add them. And here I create a new class that I call pre. And then I will do the same thing for the post-treatment variables as well. And here it's helpful when you have kind of systematically named the variables, then you can very easily find them via the search function. Properties, classes, add, and I create a new class, post. Okay, and in fact, there are two variables that I haven't labeled properly, that is age and gender, because these are clearly also pre-treatment variables. So I'll just highlight those separately and add them to the pre-class. So now it's given that I've created it before, it's now available, and I simply add them to this class pre. Okay, still the screen doesn't look any prettier, but I can improve upon that by assigning colors to these classes. I'm now through the contextual menu. I bring up the node editor, highlight my two classes, pre and post, select color, automatically assign colors to classes, and now we have them kind of colored according to their class membership. Okay, you'll see one node that is not assigned, that is the scan type. That is our treatment variable that doesn't really belong into either class. Now, here again, they're not arranged in the way we would perhaps think about this problem domain. I did some pre-work here and arranged them nicely in vertical columns, and I saved positions. I saved the screen positions, and I'm now retrieving that. I associate a node dictionary for node locations. I'm bringing that up. And so now my nodes are rearranged in columns. On the left, I have all my pre-treatment variables, my pre-treatment nodes. In the middle, at the top, I have scan type, my treatment variable. And then on the right, I have all my post-treatment variables. At the very top is the sum. That's the one that captures the sum of all these variables. And that's what we want to use as our target node. I forgot one thing, and that is, even though I have defined pre and post variables as classes, I need to formally tell BayesiaLab that I want to make the post treatment variables non-confounders. That's what I will do now. I will select the whole class. I will select the class post, and now add this class to a predefined class, the class of non-confounders. So all these nodes will be members of two classes. One is the one I defined just for convenience, for coloring purposes, and the one that BayesiaLab understands and interprets as we need to treat these as non-confounders. So properties, classes, add, and here I now select the predefined class non-confounder. So all my post-treatment variables are declared as non-confounders, and I can now proceed to machine learning. In fact, I could have machine learned first and then define the classes. The sequence doesn't matter here. Let's now proceed to machine learning. We want to learn a model, a statistical model that is targeted towards the total cost. And one thing I will do to influence that learning, I will lower the local structural coefficient of scan type. And the reason is here that I really want to make sure that I have very good connectivity in this model between scan type and all the confounders. I really want to make sure that I'm appropriately matching on the confounder, and so I'm actively lowering the threshold for discovery for that particular node. So with that, I proceed to learning. Here, without further explanation, I will learn an augmented naive Bayes network, and here is the result. So here is now our statistical model, our Bayesian network model. And of course, when we look at these arcs, clearly that's clearly not causal. In fact, here all the arcs point away from total sum, and we want to clearly compute the effect of scan type towards total sum. But given that we have encoded our theory through the selection of confounders and non-confounders, we don't have to worry about it. Rather, we can switch into the validation mode, highlight scan type, and then run our target direct effects analysis. So I'll run that here. And here are BayesiaLab tells us all the confounders that were defined. Let me scroll down to see the result. And lo and behold, we now see that scan type here in this case, CT was coded as 0 and MRI scan was coded as 1. Our unit effect is minus 340. So we have a given the use of MRI scans, we have lowered the total cost, the total treatment, post-treatment cost by $340. So that would be the conclusion of this analysis if this were real data. Of course, we can't make that statement. This is, of course, fictional data. But here you now conceptually see how that analysis works. We could furthermore now say, well, perhaps MRI scans don't work equally well for all conditions. Perhaps for mental disorders or skin disorders, MRIs really provide no benefit. So in that case, what I will do is I will compute the effect for my ICD-9 category separately. For instance, I will select neoplasms as my target node. I will exclude, hold on, I need to remove that. I will exclude the total variable and now relearn my model, augmented naive Bayes. Okay, now I've learned a new model and I repeat the same analysis again. Select scan type. Oops, I need to go into the validation mode. Scan type, report, target, direct effects on target. And now we can see what the effect is just on these ICD-9 codes. So here we have an effect of close to minus $400. It seems like in this category, there may, after all, be a benefit of using a MRI scan over a CT scan. Of course, not considering what the actual cost premium is. I don't know how much more an MRI scan costs versus a CT scan. So that brings us to the conclusion of this example, and allow me to quickly take you back into PowerPoint. Okay, let me just make a few concluding remarks. Most importantly, I would like to invite you to some of our upcoming events. We have a seminar in Toronto, not a webinar, a physical seminar, and this will be on a similar topic. It will also be about health economics and public policy research, but we will have quite a few more examples and sort of different aspects all around healthcare. On June 19, we're going into financial data. We will have a seminar in downtown Chicago in the Loop. I think we have already spoken about Chicago a few times today, so we'll be back in Chicago. June 29th, a webinar about probabilistic latent factor induction, factor analysis ultimately. July 13th, we will get into technical fault diagnosis with Bayesian networks, very interesting topic. And then finally, on July 27th, we get into military strategy with the topic of adversarial reasoning. That should be very interesting. Now, for those of you who are interested in really using BayesiaLab for your researchers, for your research, for your daily work, we have 3-day courses that we host on a regular basis around the world. The next course in the US will be on June 25th through 27th in Boston. Then in July, we have a course in San Francisco, then London, New Delhi, back in Chicago, and then finally at the end of the year, we have one in New York. Most of you will already know we have trial versions of BayesiaLab that allow you to experiment with all the examples, such as the ones I shared with you today. And then, of course, we have our forum, our online forum, which is a great place to raise technical questions, share tips and tricks and tips with other BayesiaLab users. And allow me to mention Chicago one final time today. That's where we have our annual conference, November 1st and 2nd, right on Michigan Avenue near the John Hancock Tower. We have a great venue. We expect a lot of interesting guests, a lot of great speakers. So please put it into your calendar. You should receive formal invitations fairly shortly, and I hope you can join us there. So with that, that brings us to the end of today's webinar. On behalf of our team, I'd like to thank you for your time and interest. Please do feel free to reach out to us with questions that you may have about Bayesian networks or BayesiaLab. We'd be very happy to speak to you one-on-one about use cases, potential use cases that you may have for our technology. So thanks again. I hope to see you at our next event, and have a great weekend.